Today we're going to look at something that helps us understand why this calculus stuff we've been doing, this derivative stuff, can actually find some pretty interesting pieces of information that we typically are dependent on our calculator for. Now, I had a great website to show this in class. It's going to be a little trickier, a little messier here, but I want you to think about this tangent line that we've been dealing with and its slope. And think about when that slope is positive, or when it's negative, or when it's 0. So I had some sort of a graph that was kind of wavy and fun like that, and just a polynomial graph, and I want you to look and see. If I were to pick this spot right here and draw the tangent line to it, it would look something like this. And the slope of that line would be positive. And then we kind of scrolled along this function and picked a new spot and said, what about this line right here? Okay, that's still positive. Okay, remember, we're looking at when is the slope positive, negative, 0. Right here, it would be something like that-ish. Okay, that's good, still positive. But what's going to happen when you get to that peak right there and you try to draw a tangent line? Well, it's not a point, so it's not that no limit thing, or it's really just going to end up being like a horizontal tangent line. Okay, well, let's keep on going. What if it was here? Well, now all of a sudden this tangent line is going to flip this way, and then it's going to continue on and be a little bit more like, that's not very good. Let me undo that one, because that's actually going to end up, well, to be honest with you, I went far enough on this that I think my tangent line is going to end up underneath that curve now. And we'll talk about why that's important in a minute. But now my tangent line is here. And then let's go to that minimum spot. And now the tangent line is going to be horizontal. And then you work your way back over here. And we were just scrolling around and we grabbed that tangent line and made it right along the side of that function to see what it was going to do always. All right, so let's look at this. That's pretty messy, huh? If the derivative is equal to 0, so if the slope is equal to 0, that's a horizontal line. Horizontal lines have slope 0. What's going on the function when I add a horizontal tangent line? Oh, okay, that happens at a max or. So that's kind of an important deal if you think about it. You go find the derivative, you find out the derivative equals 0, right then you know that's a maximum or a minimum spot. Okay, we always went to our calculator to find the max or the min. Now we have a way to actually find out the max or min and just do it with the derivative rather than having to have a calculator for it. Now let's look at the other side of this. What did you notice about all the ones that had a positive slope? So think of that was all these first ones. They all had positive slope. And then it hit that max, and then it started having a negative slope. And then it was back to a min, and now we were back to a positive slope. What's going on our function so that those tangent lines have positive slopes? And hopefully you can kind of see that. Well, that's going to happen every time the function is increasing, when it's headed upward. So that's going to happen when the function is increasing. And then the negative ones are going to happen, that all happened like in this chunk, when it was decreasing. We can then use that information to find out some stuff about our function without having to actually graph it or find anything through the calculator. And that's what we're practicing today. These things that we're finding here using the calculus information is what we call the critical points. They're critical points in the graph. The max and the min, those are critical spots. So that's one of the things. And then, of course, we'll do the increasing and decreasing. But there is another critical point. We call it the point of inflection. And we'll talk about that in a few slides. But the critical points can be found using the derivative. That's what we're doing. Now, I gave you a function here, decided to make it a cubic. It's a nice polynomial function. Let's start off and let's find the derivative. Now, since it's a nice polynomial function, we're going to be using the power rule to find the derivative. Looks like we would have a 3x squared minus 10x minus 8. That's the derivative. All right, now remember that when the derivative was equal to 0, then you had that horizontal tangent, and we knew that that was going to be a max or min. That's what we're going to do. We're going to take the derivative and we're going to make it equal 0. And we're going to solve for x. We're going to figure out what x value will make that slope be 0. Looks like a nice factoring problem. Um, 4 and 2, we'll have a negative there, positive. Looks like x is going to equal negative 2/3 and 4. Now these are the x values of the min and the max, negative 2/3 and at 4. So my function then will have a max or a min at those two spots. But that's not an ordered pair, those are both x's. You need to plug each one of those into the function, back into the original function up here, to see what the matching y value on that function would be. So let's plug in 4. I'm going to find, oh, okay, so maybe I need to find something else out first because it says max and min. Which one of those is going to be the max and which is going to be the min? You have to be a little bit careful. Don't automatically say the negative would be the min. You have to think about what you know about these graphs and should always have that in the back of your mind as you're doing these problems. This is a cubic. You should know that a cubic does this. Starts low, comes up, has a max, and then has a min. So this spot right here is the max, and it would happen actually prior to the minimum as you read the graph left to right. When I look at this, the x value that I would hit first would be the max. The x value that I'd hit next would be the min. That means when I look at it left to right, this is going to be the maximum, this is going to be the minimum. So we'll go over here, we're going to find f of negative 2/3. That means in your calculator, and I'll let you calculate that, put in negative 2/3 and cube it, minus 5, negative 2/3 and square it, and so forth. Same thing then on the minimum. You're going to go find f of 4 to see what that is. And so 4 cubed, we can probably do this one a little bit easier in our head. 4 cubed is going to be 64 minus 5 times 16, so that's 80, minus 32 plus 2. Okay, so that looks like what? You'd have a... Alright, I might go to my calculator. I'm going to cheat. 64 minus the 80. And I got negative 46. So the minimum, the ordered pair for the minimum is actually then going to be 4, negative 46. Obviously then my graph would be way, I mean that shows it didn't go very low, but it would be way, way, way down there a ways. Okay, I'll let you go ahead and plug in negative 2/3 to see what the maximum ordered pair would be. And so it would be a negative 2/3 and then whatever you get when you plug that in. All right, I did the work for you. I went ahead and put it in, and I got a 4.8 for a y value on that. All right, let's keep moving. The other part that we can determine from that derivative is where the function is headed up and where it's headed down. Where does the function increase and where does it decrease? Now you sort of know that if you already know what the function looks like, but a lot of times we're going to get a function that we don't know what it looks like, and we can still figure out where it's increasing and decreasing, and we could start to make this graph if we knew some of this key information. So this says use the x values from the max and the min to create a sign chart. Okay, and by a sign chart, I kind of mean way back when we did inequalities. And so in that particular example, I had a negative 2/3 and I had a 4. And then what I'm going to do is I'm going to plug values from each area. So I'm going to plug in a value that falls out here, a value that falls in between those x's, and a value out here. and I'm going to see what I get back. Now what I'm doing is I'm plugging it into the derivative function. I want to plug it into the derivative function to see if it's positive or if it's negative at that spot. If the derivative is positive, remember that the function is going to be increasing. That's what it's going to tell us. Positive slope will be increasing, and if the derivative is negative, then it's going to be decreasing. So let's try it. There's my derivative function. I'm going to pick some number over in this area. Pick something that's easy to plug in. I could put in a -1. That'd be pretty easy, and it would be on this side of that mark. I'm going to then, okay, so then I come over here and I'm going to do f of -1. Well, that would become 3, then a +10, and a -8. And that ends up getting me 5. Well, that's positive right here. That's positive. So any value over there is positive, meaning that that is where my function is going to be increasing. Next, I'm going to put in a number that falls in between here. 0 would be super easy. That's going to just be -8. Oh, look, the derivative is negative in that area. That means my function is going to be decreasing from there. Now let's plug in another number. Looks like I'm going to probably plug in 5 for that space over to the right of my 4. And so that's going to be 25 times 3, and then -50 and -8. And here's the thing. I mean, I can figure out what that equals, but in the end, all I'm really concerned about is if that is positive or if that is negative, and I can tell that 75 is bigger than -58. That's going to end up being positive. All right, so what I've learned then is that I'm going to have a maximum at -2/3. I'm going to have a minimum at 4, and I know that my function is going to increase until it gets to that maximum. It's going to turn around and decrease until it gets to the 4. Now remember, these are the x values because I'm reading it left to right, and then my function is going to be increasing again. So you get a feel for what's happening with that function, even if you're not familiar with what it looks like. All right, then we have one other thing. We have what we call the point of inflection. The point of inflection is where the function switches concavity. When you look at this, and I had a graph, I'll just draw something here. And when it comes up and down and up, and concavity means that, like right here, this is concave down, right here, but this is concave up, right here. So somewhere in here, it switches that concavity. Also what happened, that's when my tangent line, where it was above the graph, or above the curve, above the curve, above the curve, but if I get far enough, now my tangent line is below the curve, below the curve, below the curve. So that's what happens at that point of inflection. To find the point of inflection, which is going to fall somewhere in here, it doesn't always have to be right in the middle, it just varies on the function, but to find it, we're going to find what we call the second derivative. That's the derivative of the derivative. Okay, we still just use the power rule to do it, so our derivative, if you'll recall, was 3x squared minus 10x minus 8. Now, what we're going to do is find the second derivative. We notate that with 2 little hash marks, the second derivative. And it's just the derivative of the derivative, so that'd be 6x minus 10 using the power rule. And then once I do that, that point of inflection happens whenever the second derivative is equal to 0. Well, let's set it equal to 0 then. Add the 10 and divide by the 6. That's going to be 10/6, or 5/3 if we reduce it. That's going to be the x value where that occurs. Now, I want to have an ordered pair, though, for where it occurs, so I need its matching y value from the function. So it goes back into f of x, back into the original to find its matching y value. So you have to go back to the original function, is x cubed minus 5x squared minus 8x plus 2. Okay, now I'm going to take this 5/3 right here and I'm going to plug it in there and there and there to see what I get. Now, one of the things that I did, what I did on that last one, when I just did it for you, I actually stored my fraction as a variable. So what I'm going to do is I'm going to take 5 divided by 3, and I'm going to store it. As alpha A. And then I'm just going to go back up when I used it previously and re-evaluate that. That's just my little trick. I don't know. You don't have to do that. You can just type it in. I don't know that it saved me that much time. All right, so what I'm doing here is I'm finding f of 5/3, and I got negative 20.6. I'll just go with that. So the ordered pair where that occurs is at 5/3, negative 20.6. That's called the point of inflection. Today what we've focused on then is finding what we call critical points in our graph. The critical points are the max and the min and the point of inflection. We also can use the derivative to help us see where the function increases and decreases. But ultimately when we say find the critical points, we mean the min and the max and the point of inflection. And this slide is just a summary of how do you do each one of those things. You find the derivative, you set it equal to 0. I don't need to read through this for you. You use this to help you summarize. So when it asks you to do something on your instructions, you know which of these things you were doing. All right, good luck.